Okay, so good evening, everyone. Today I'm going to present the paper titled YOLObile, a real-time object detection on mobile devices through compression, compilation, co-design. And this is the paper that published in AAAI this year. And here is today's outlines. First, I will introduce the background and the motivation, and then I will present their proposed framework, including three type of design, and then I will show you the experiment results. So first, the object detection has been widely used in various of the applications, such as the auto driving. We need to identify the incoming vehicles or the traffic signals, and also they are widely used in the UAV obstacle avoidance and some augmented reality and inventory management showing in the pictures. And thanks for the deep learning technologies, the object detection task can achieve high accuracy. However, one remaining challenge is that due to the large scale of the current DN models, even for the DN inference can be difficult to implement on the devices due to the high computation and the storage demands. Let's see, for example, here we show some of the state-of-art, the object detection algorithms, such as the SSD and the YOLO. As you can see, they can achieve a very high model accuracy, but the performance in terms of the frame per second to process the image can be very slow due to the large networks they use. So to deal with this challenge, the author in the YOLO groups had proposed the tiny website, the networks that sacrifice the accuracy to reduce the network size to implement on the mobile device. You can see, although the FPS is increased, but the model accuracy can drop very large. So current objective detection algorithm can still not achieve the real-time performance with this high accuracy. So in this paper, they're trying to solve this problem by proposing new schemes. So one of the ways to reduce the large DN model size is to use the pruning. And specific, this paper is targeted on the weight prunings. So the pruning can actually divide into two kind of methods. One is called the non-structured weight pruning. And you can see in these figures, we showed the weight matrix in one of the layers. And the non-structured pruning usually depends on the values or the importance of the different weights to prune the redundant weight in each of the layers. And since this fine-grained pruning, we can actually achieve the same accuracy as the original networks. But this unstructured pruning actually is very difficult to implement in the real-world design, because in order to save the sparse, the matrix, we need to store the index. And due to the unstructured properties, the storage of storing this index can be very huge, and that causes the speed degradation in the modern GPU and CPUs. So another approach to deal with this challenge is called the structured pruning. It's very hardware friendly, since we can see for this 2D weight matrix, we can either prune the entire filters in each layers, or we can prune each channel of all the filters, so that it can have the clear structures to do the computation and to save the storage there. However, so for the filter pruning, because we prune the entire filters, so according to the convolutional operations, you can see the output is that you can skip the computing and the storage for if we can prune the total number of key filters in this layer, we can skip the computing and the storage of the feature map in the L+1. This is the output feature map. And for the channel pruning, actually, we can reduce the computing and the data loading for the input feature map if we can prune the P number of the channels. So according to this kind of coarse pruning, we can cause a large accuracy loss based on this method. And until recently,
I have a quick conceptual question. So the channel pruning here, the channel, is it the wireless channel we talk about, or
no.
Where,
it's not. It's like here. You can see actually for feature map, they have a 3-dimension. It means that you have like n feature map here. So the channel just means how number of how can we say this trunk actually is a kernel. If you can see here, each map is a kernel. So the number of kernels is the number of channel in the neural networks they call.
So how about filter?
Filter is this cube.
Filter is the whole cube.
Yeah, it just show here. This row actually is one of the filter.
Okay.
And so 3-dimension is look like this.
So say the filters look like the row and apply to all the channels, right?
Yeah.
So you say if you eliminate filter 1, that means for all channels, row 1 will be eliminated.
Yes. Okay. So here, the white one, it just show that this whole channel.
The channel is like more horizontal. Okay.
Yeah.
Vertical.
Output is different here.
Okay. Yeah. Okay. Go ahead, please.
So the reason new method called the pattern-based weight pruning actually is to solve the drawback of the previous 2 methods. So what they do is that they introduce the kernel patterns as the new pruning strategies. So the kernel in each filter, actually you can prune based on this predetermined the patterns libraries. And to do that, so the benefit of doing the pattern pruning is that you can have the limited number of the kernel patterns if we fix the pruning ratios. So for example here, if we want to say keep only 4 weights in these 3x3 kernels, so we can have the limited number of these patterns in these 3x3 convolutional layers. And in these ways, so you can easily create the index for different patterns, and also for the kernels with share the same pattern, you can group them together to do the computing. In this case, the pattern-based can be very hardware friendly. And in terms of the model accuracy, actually, this type of kernel pattern, you can also interpret as the sparse convolutional patterns. This is a special computation vision areas. So you can use this Gaussian or Laplace filters to create the certain sparse patterns for different kernels. And this Gaussian and Laplace filter is originally used for the image smoothness or the image sharpness to increase the image quality, so that using the specific design pattern, we can recover or even improve the model accuracy and avoid the overfitting. So this kind of pattern-based pruning can achieve the high accuracy and the hardware-friendly models. However, this specific design based on the filters can only apply in these 3x3 convolutional layers. And in this case, if we want to achieve a large compression ratios, we can only prune the weight in the convolutional layer and cause a large accuracy loss. Yes.
Quick question, because it's a totally new area for, at least for me, right? So for this pattern, from the graphical presentation, I can understand if there are two rectangular one, right? So I mean the left side two rectangular one, square one, I would say. So you know, their index, the index, the easy presentation of index, you means after pruning is some simple way to, okay. So I can understand two square one, their index probably the same. But for the T-shaped one, why is T-shape up? Why is T-shape down? So do we keep the same index for this two? Or do we have another, you know, I don't know, index or whatever symbol to represent the T-shape up or T-shape down?
I think they need to design that.
We need to introduce another notation to represent this.
Yeah, probably one to introduce the direction or something. I think.
Oh, okay.
Yeah.
But still, it saves a lot of memory space, right? And a lot of computing complexity. Yeah.
Yes, because the pattern is limited number. So the pattern is definitely be more efficient compared with the unstructured one.
Okay.
Yes.
So, okay. The kernel we're talking about it just like one layer or something, right? Or
it's actually in the one feature filter. Sorry. So you can see this cube, actually they have multiple kernels. They combine together, they call the filters. So we do not completely to eliminate the entire filter, but we just can keep some of the value here. So it's this kind of design can be seen as between the unstructured and the structured.
Okay, okay. Okay, thank you. Please more.
Yeah. So because of the limitation that this type of pattern pruning can only apply in these 3x3 layers and cause a lot of loss when we need a large compression rate. So in this paper, they try to design a new pruning method called the block punched pruning that can be applied in different type of layer with different kernel size. And also they try to design a efficient computing method to further speed up the inference. And next, we'll see the framework overview. So the block punched pruning actually, if we can see the entire weight in each of the layer as this large map, the blockchain actually just to divided this weight metric into multiple blocks. And within each blocks, their pruning strategy will be the same. And we can prune the same location in all the kernels within the blocks. And for different blocks, we can use different pruning design. So it can be more flexible to introduce for used in different kernel size and in different layers. And also by properly select the block size, we can choose the different pruning patterns more flexible, because this pruning pattern actually is set manually depending on how many blocks you are set in different layers. So the block size will be important to trade off the hardware parallelism and the model accuracies. So the author is trying to give some guideline about how to design this block size. And for the block channels, actually, it only depends on the hardware you are using, because for the convolutional layer operation, actually, you will use the input feature map to multiply with one filter to obtain the one output feature map. So the input channel will be depending on how long the registration you need. So because when you do the convolutional operations, actually you need to multiply So for each of the channels within one filters, each kernel here, you need to multiply with the input feature map, and you need to sum the values for all the channels. So once you can read the multiple channels within these registrations, it just depending on the computational capacity in the threading of the GPU and the CPU here. So even if you increase the channel in the block size, you cannot improve the computing time. And for the filter, it actually depending on the trade-off between the accuracy and the hardware accelerator, because multiple filters, it means the multiple threading tasks. So increase the number of filters, you can do more parallel computing. But increase the filter, actually, you increase this block size to create less patterns, and it probably can degrade the model accuracy. So they do the experiment result in here. And as you can see, 4 here represented the channel, basically depending on the hardware. And if you can increase the filters, you can see, although the computing is can significantly the performance, it can be significantly increased, but the accuracy is dropped. So usually depending on the different device, you will need to do several experiments to determine the best number of the filters you used for the block size here. And this is the
here is the number of filters or is the number of channels?
This for the second one is means the channel.
For the channel. Okay.
Yeah, the first one is the filters.
Number of filters.
Yes.
Okay. Well, I didn't remember exactly, but I teach micro P class. So can we create an unlimited multi-threading? I remember we can probably create some virtual multi-thread, right?
Mm-hmm. I don't think unlimited.
Not unlimited, right? Okay.
Yeah.
Okay. All right, thank you.
So here is the selection of the block. And next, they will introduce the regularization terms to do the block pruning. So actually, we formulate the pruning problem as follow. Here we have the loss function used for the training, and also we introduce the lambda to control the trade-off between the accuracy and the sparsification of the models. And this R is represented the regularization terms. So in order to do the pruning, use the block punching schemes. Actually, we were first decompose this weight into total K blocks, and using this weighted group loss regularization to the formulation is as follows. And we use this reweighted term alpha to penalize the value, the weight with smaller values by using this 1 over the F norms terms here. So if this, if the value of this weight is very small, so the alpha will be pretty large. And to avoid the 0, so we add a small number epsilon here. So we can penalize the weight with smaller size to obtain the pruning strategies. So this alpha actually is set the same in each blocks, and different blocks will have different alpha. And to do this pruning, actually, we need to use a pre-trained model. Actually, for most of the pruning papers, you basically trained your model in the later stage, and you introduce these regularization terms to retrain several iterations and determine the pruned weight, and you will retrain again to recover the accuracy. So this is the overall pruning process they consider in this paper. And also for the, so next they were talking about some computer hardware design to accelerate the inference. First is called the compilers access the accelerator. Is because we designed the weight matrix in following ways. So you can see some of the filter actually share the similar structures. So what they do is they can reorder the computing orders in different filters and group them together so that we can have more efficient computing, parallelism, and the storage in here. And the benefit of introducing the compiler to accelerate this type of scheme is that it can be efficiently applied in the current commercial mobile GPU and CPU. So we do not need some specific hardware requirement for this. And the next is the mobile GPU and CPU collaborative. It's because that usually in the mobile devices, such as the smartphone, we usually have the CPU and GPU can be both used for the inference. For example, this design is particularly designed for the YOLObile. So in the YOLObile, actually, depending on the network structure, they have different, for the same input, they have 2 branches of the computing. So you can see, for example, for branch 1, most of the computing, including the convolutional operations. So we can assign this type of computing task to the GPU. And for the branch 2, we can determine whether it's more efficient to process on the GPU or process on the CPUs. So they come up with the following device selections based on the latency. It's basically just to compute the time if we using the GPU or using the CPU plus GPU to do the computing in the branch 2. So depending on different design, you can do this offline scheduling to determine the different operation in different GPU or CPUs to further.
Hello, Ray. So
yeah,
what is exactly for the branch 1 and branch 2?
Oh, this is because the YOLO has such kind of design, kind of improve the network accuracy. This is the particular design, like such as the ResNet, they have 2 type of branch in here, so they can introduce this kind of cross-stage partial to do the objective detections.
So what is inside the branch 1 or branch 2? Is different partitions of data, or different features, or
different features, like you have the layers. So for branch one, so for the same input, I believe it's like the image they want to detect. So for example, the branch one will be to do the classification. We have multiple layers to extract the features to do the classification. And branch two, probably they do the objective detection to locate the area of this object. So they kind of have two different network architecture here.
So it's like it's more like a ensemble learning. It involves like two different learning tasks.
Yeah, I think.
So the question is, when we have these two branches, we wanted to parallelize them to GPU and CPU, right?
Yeah.
Then how can we guarantee, the CPU and the GPU can finish the amount of work, roughly at the same time, right? So otherwise, the GPU has to wait for the CPU, or the CPU has to wait for the GPU.
Yes, yes.
So we are working on a project trying to parallelize the deep learning to GPU and the CPU. We try to do model partitioning and the data partitioning. So which means we have like a data parallelism and model parallelism, but it is hard to make sure that they can collaborate with each other smoothly. Otherwise, the CPU has to wait for GPU here.
Yeah, yeah.
Or the GPU has to wait. Most of the time, the GPU has to wait for CPU here. So how does this paper solve this problem?
Oh, okay. So I believe they do not solve this kind of problem. They provide this kind of a way to reduce. I can say it can only reduce certain kind of latency if we just only put all of this computing in the GPU only. So I think they claim is that because of the mobile CPU and GPU, they actually because of is in the mobile devices. So the CPU and GPU actually, if we can see the branch two, if the computational task is not very complicated, the CPU and actually can share the very similar performance.
Yeah, but still, even though the part of the work, in branch two is small, you can hardly guarantee the CPU will finish this amount of work before the GPU does, right?
Yeah, it's true.
Yeah, because when we study this part, we figure out there's a ratio between the amount of job assigned to CPU and the amount of job assigned to the GPU. This ratio will make sure the CPU and the GPU finish the job at the same time. But here, we don't have such a ratio. We just rely on the model structure, right? The branch one, the branch two, and if we directly assign the branch one and branch two to GPU and CPU respectively, probably they might even increase the latency if the CPU doesn't work very well.
Yeah, it's true, but
they didn't reply this question, right?
Yeah.
Okay. Okay, thank you.
Okay, so next I will introduce their experiment result. So here is the experiment setup. They use the PyTorch to achieve to implement the neural networks, and they test on the Galaxy S20s to do the real world test information for the performance in terms of the frame per second and the accuracy in here. So they use this common COCO dataset.
What is the framework, the deep learning framework on Galaxy S20? Is the PyTorch for mobile devices, or?
Yeah, the framework, you mean the network?
How they implement the you know, the neural network, the deep learning framework, like the PyTorch, like TensorFlow.
Yeah, they use PyTorch.
PyTorch for Android.
Yes. Oh, I see. It's the TF Lite.
Okay, TF Lite.
Yeah.
The TF Lite can only do inference, right?
Inference, yes.
Okay.
Here they also test for the inference.
Okay, I see.
It's on the RTX.
Okay.
Yeah, they only do the inference task on this Galaxy smartphones, and also there are two evaluation matrix here. So they use the mean average precision to do the accuracy performance on the multi-labels in the object detections. So the intersects over the unit represented in here, it shows the, the accuracy of the location for each object. So here is their performance evaluation. As you can see, they compare with this existing state of art, the object detection algorithms, and you can see the YOLObile achieved the smallest. I'm sorry. They can have the high accuracy as well as the high performance in here. And this backbone means that they do the feature extraction using the following networks. I think if it's not, it means that the kernel net is using the same to extract the features. And yeah, it also shows the effectiveness of the proposed methods. And also using this map, you can see the proposed method can achieve the best trade-off between the performance and the model accuracy. And then they will test for different kind of compression rate. And as you can see, the model accuracy degree very small, but the performance can be increased largely. And then they also compared with different pruning strategies. As you can see, with the same type of pruning ratios, their proposed method can have the best best accuracy and the trade-off between the accuracy and the performance as well. And they also compare with the pattern-based pruning. As you can see, the proposed method can achieve the small accuracy degree even when we increase the compression rate to very large numbers. But for the pattern pruning, since they can only prune on the convolutional layers, so if the compression rate is very large, the accuracy will drop very, very quickly. And yeah, that's it. And here they just summarize their contributions. So this is the work they are done. And thank you. Any question?